Now, to solve a differential equation using the separation of variables, well, this is actually going to be very straightforward. And if it works, you really want to take advantage of this technique because it's actually quite handy when it actually works. It doesn't always work, but if it works, you really want to take advantage of it. Take, for instance, you have a differential equation dy. I'll use the linear differential equation here, dx. And let's say this is just equal to, we can say maybe just some function of x. We can say maybe p of x. And then maybe this multiplies something here, a function of y. So let's say q of y. Now, by separation of variables, what you want to do here is you want to split this into the left side and the right side. Now, the idea here is that everything on one side must have an x, and everything on the other side must have a y. You want to separate this into two sides, and each side must only have the respective variable. That's why this is the separation of variables. You want to separate them. The first part, for example, is to separate these, the dy and the dx. You want dy to be on one side and dx to be on the other. So I will just multiply everything by dx so that on the left side, I remain with dy. On the right side, now I'll have this, and then this, and then dx comes this side. Now I see that on my left side, I now have dy. On the right side, I now have dx. And you really want to have the dx and the dy to be in the numerator. You don't want them to be in the denominator, even though I've said that you want dx to be on one side, dy to be on the other. You really want them to be in the numerator, not in the denominator. Once you have done that, you now want to make sure that, okay, where there is dy, that is where the variable, any term that is going to have a y must be with dy. And on the left, yeah, that's the right. The right-hand side must only have terms that have an x. And since p of x here is going to be a function that only has x and maybe some constants there, then this has to be with dx. And q of y here has a y, it has to be with dy. So in this case, it implies that you have to divide both sides by q of y, which will eliminate it this side and introduce it this side. So this is now where you end up. Once you have reached this part, you now have two expressions. The left side is a function of y. The right side is a function of x. Now, once you've reached this part, you can now integrate both sides respectively. The left-hand side will be with respect to y. The right-hand side will be with respect to x. So ideally, this is how separation of variables work. And from here, you'll see that you'll be able, of course, these are going to be expressions whose integrals you can actually evaluate, maybe using some tricks or sometimes just directly. So in simple terms, this is how it is going to work. So after you're done with this, you have to make y the subject of the formula, then equals to something. And if you're not given initial conditions, then you know to say you have to introduce some constant of integration. If you have initial conditions or boundary conditions, you can figure out what that constant there is going to be. For our examples here, we're going to deal with one where we're not given the boundary conditions. But if we find a question with boundary conditions, we're going to demonstrate how that's going to be worked out. Let's look at a real example and see how this concludes. Consider this example. So in this case, we want to solve the following ODEs using the separation of variables. So how does it go? Well, look at the first example. Here we have dy over dx, and then we have 5x, and then we have 7y. Now, like I mentioned, you really just want to have everything with an x on one side, everything with a y on the other. So the first step here might be to cross multiply. You can look at it as cross multiplication, or you can say multiply everything by dx so that you eliminate dx this side. But eventually you have to multiply everything by also 7y, or even just y. It doesn't matter whether you say 7y or y, it will still just be the same thing. But I'll say let's cross multiply here. And if we cross multiply, we're going to end up with 7y this side, and then we have dy. Then the other side, we're going to have 5x, and then dx this side. Once you're done with this part, notice that just doing this, we already have everything with an x on the right side, everything with a y on the left. So we can now integrate both sides. So if we still had a y here, we would have been forced to try to get rid of it before using this, before going on to the next step. So here we can integrate this. So 7 here is a constant, so you can bring it out. We just have the integral of y with respect to y. 5 here is also a constant. I forgot that y placed there. So 5 here is a constant, so this is just x dx. So you perform the integral now. The integral of y with respect to y is going to be 7. Then the integral here is going to be y to the power 2 over 2. And then here, this is going to be 5. And then x there, this is going to be x squared over 2 as well. And since we're done integrating, we can now introduce a constant of integration. Again, in cases where you're given the initial condition, after performing integration like this, the next part would be to figure out what that c is, so that then you bring it back to the equation and then you have something normal. But if we're not given the initial conditions, then the constant is going to remain. Okay, so this part is done. We can now just simplify this expression so that we get the equation for y. Okay, so yeah, everything's okay here. So how does this simplify? So this is, of course, just 7. Then we have 2y squared is equals to 5 over 2. And then we have x squared plus c. Multiply through by 2, we have 7 y squared is equals to 5 x squared plus 2c. Of course, this just remains a constant, doesn't really change much. So you can even say another constant. Can you say the first one was c1, now this is c2, just a constant. So here, of course, divide through by 7 now. Y squared is now equals to 5 over 7, x squared plus 2c over 7. Finally, y will have to be equal to the square root of 5 over 7 x squared plus 2c over 7. So this becomes the expression for y. So you can say, of course, plus or minus here, but you can still just leave it like that. Sometimes, though, you might have to say plus or minus there. Okay, so again, one more comment about this term here. Notice that this term still is a constant. So I can say that, okay, maybe the constant I introduced here was C1. So this is C1, this is C1, this is C1. So by the end of it all, I can now say that, okay, this whole thing is now C. So where C is actually equals to that 2C1 over 7. So this is another way of looking at it. You can still do that. But I'll keep that C there the way it was. Okay, so this becomes the solution. Any questions there? Okay, let's look at another one. Look at the second one there where we have dy, dx, when. What's the question there? Boyd, finish your question.
I'm saying integrating the left side and the right side. Why did you add the constant to the left side as well?
Okay. So it's the same case really. A constant is a constant. And yeah, let me do it like this. Ideally, even if I was to add another constant on the left side, when those constants add up or when they subtract, don't you agree that they will just give us the same constant? They'll just give us another constant, not the same, another constant. Do you get that? Like, where's that step? Somewhere here. Had I added another constant this side, C2, the idea here is that I can now bring this C2 and this C1 and say, okay, let me take them to the right-hand side. So on the right-hand side, I'll now have C2 minus C1. Don't you see that this will also just be a constant C?
Yes, I see.
Yeah, so this is why we only add one constant on one side, because whether you add another constant on the other side, a constant and a constant will reduce to just a constant. So it will still be a constant. It's the same reason why I say that this term here, I can say, okay, this is also a constant, and I can just put a K there to say it's another constant there. Okay, so with that done, look at this one. For this one as well, just the same approach. You want everything with X on one side, everything with Y on the other. I'll cross multiply here so that I have 1 plus X squared multiplying dy equal to 1 plus y squared multiplying dx. But when you look at the expression that we have, everything with x is with y, and everything with y here, it is with x. So you really don't want this version. You want to rearrange them. One mistake that I've seen, I think, with some students is that you want to distribute the dy here. Distributing the dy is going to just bring another complication. It will be hard for you to actually separate and bring it back. You'd have to come back to this step. Instead, just divide. Divide this side by 1 plus y to get rid of the y. You can't just divide with y. Notice that y squared moves with 1. It's a full package there. So I have to divide with 1 plus y squared. So I'll do the same thing here. 1 plus y squared. Notice that this eliminates 1 plus y squared this side, but it remains on the left-hand side where I have dy. You do the same thing with the 1 plus x squared. Divided both sides. It shifts from the left side to the right side. So in the end, I have 1 over 1 plus y squared dy equal to 1 over 1 plus x squared dx. So we now reach this part or this stage. Now you can easily integrate the left side and the right side because everything here is with respect to y or a constant, even here with respect to x or a constant, which is what we wanted. Now we have to integrate. But before I leave that midway, how would you integrate such expressions? How do you perform the integrals of those? Yes. So here to integrate these, you can now use that tan substitution. So are you guys comfortable with tan substitution or you'd want a demo? Kango, I didn't get that.
Go ahead with the demo.
Okay, so we're going to work out this expression. You have to see that the other expression is of the same format. So whatever the solution I will find for this, I'll just change and use x, and that will be the same solution on the right side as well. So let's solve this. Let's work out this integral using tan substitution. So for that part, I'll just highlight that part I'm just looking at. I'll keep everything else on the other part, on the right side. Just say let y be equal to, the first part is a 1. Had it been a number, I would have just said the square root of that number, then tan. So this is just going to be 1 tan theta. So if y is equals to tan theta, then dy will have to be equal to sec squared theta d theta. So the two things that you needed. Now you can make the substitution. That expression becomes 1 over 1 plus, where we have tan, where we have y squared, it becomes tan squared theta. Then where we have dy here, where we have dy, we're going to put that expression, sec squared theta d theta. Again here, remember I did emphasize, had this been maybe a 4 plus y squared, then my y would have been equal to 2 tan theta. I hope you guys remember this. I think we spent a bit of time doing this. Okay, but let's continue with our problem. So having reached this part, you'd have to, of course, the right-hand side, I haven't touched it yet. I know it will integrate using the same format, seeing that they literally look the same. So I'll keep it like this for now, and then I'll just drop it later. Okay, so here we are. So at this point, you have to remember that part 1 plus tan squared theta is equal to sec squared theta. What does this mean? This is the same as that from this identity. So you have to remember this identity. So this implies that you're basically just looking at the integral of d theta. On the right side, you also just have this. So the integral of d theta there is just going to be theta. So we bring back what theta was. So remember, what we had was y being equal to tan. So is there another way of integrating without using tan sub? Sadly, for such expressions, tan is the best approach. Of course, there are always many ways of doing it. There might be another method. If you guys have stumbled across it, feel free to share, but tan is usually what is used there. So we had tan theta here. This implies that theta has to be equal to tan inverse of y. So that is going to be tan inverse of y. So where we have theta here, we're going to put tan inverse of y. So we had theta here, we're going to have tan inverse of y equal to, on the right side, we still have this part. Okay, this is where we are now. We have solved or integrated the left side. Now we want to integrate the right side using the same approach. Now you guys can actually predict what the right-hand side is going to look like based on how the left-hand side turned out, since they are one and the same expression. They're similar. The only difference is what you have is an x. So what will be the solution on the left side? It's going to be what? Tan inverse. Yes. This is going to be tan inverse of x. So since we're done integrating, this is going to be plus c. Now, once we've reached this part, the solution has to be y is equal to, not tan inverse of y. Luckily for us, trying to do that, the expression becomes even much more simpler. What do I mean? Had this been tan inverse of y is equals to something like maybe, let me say, phi. Had this been the case, then you'd have to remember that for you to get an inverse, you got rid of tan somewhere here. So this implies that y has to be equal to tan phi. So this is what you'd have to recall. So to get rid of tan inverse, you know to say then y has to be something like this. But phi here represents whatever this is. So in other words, for our expression, when we get rid of the tan inverse that is with y, what you're going to end up with is going to be tan, and then everything else that is this side becomes the argument of the tan. So this will be tan inverse of the x on the first term, then plus the constant of integration there. So this becomes the solution, but it doesn't really look too good the way it is. We can simplify this a little bit further. Above, we have tan and tan inverse. What is going to be tan of tan inverse of x? What do you guys think? I'll just distribute that tan there. What is going to be tan of tan inverse of x?
X.
Yes. So tan of tan inverse of x will reduce to just x, while tan c will remain tan c. So this becomes y is equals to just x plus tan c. Again, another classic step where we say tan c, since c is a constant, tan c is also a constant. This part can also just be said, okay, maybe this was c1, it's just a constant c. So, but we'll keep it like that. So this becomes the solution to that differential equation using separation of variables. Any questions there? Now, Mapalo, you did ask to say that is there another way of performing that integral? Well, these are standard integrals. The integral of something of the form 1 over, and then you have a squared here plus x squared dx. This can be taken as a standard integral, and the solutions to these have a standard way that they come out. You can actually try to see the way our integral came out to see how this is going to look like. Do you guys know how this integral would come out? Do you know how this would come out? Yeah.
A plus x is equal to a and
A tan theta.
Yes.
Okay, so firstly, yes, you'd have to define x to be equals to A tan theta. But I'm just trying to take a shortcut where you know the solution. Like when you do this, yes, when you do this substitution, how would the solution come out? Have you memorized it? You can, it's something that we derived before, but you have to see that this will simplify to become 1 over A and then tan inverse. And then this is going to be, that is x over A. Do you remember this? If you can memorize this, Mapalo, you'd not have to go through all the hassle. Notice that if you actually made this substitution that Zumila was just giving us, notice that the x here would be A, and then this would be sec squared theta. This is what you'd have. And then after this, what else? You'd now make the substitution. This would be the integral of 1 over A squared plus A squared tan squared theta, and then A sec squared theta d theta. Observe that A can be factored out, so that you now have 1 over A squared. This is 1 over 1 plus tan squared. And then you still have the A coming with the sec there. And then like before, the sec cancels out and the 1 plus tan cancels out. The A cancels once. You now have 1 over A. And then the integral of d theta. So that in the end, this becomes 1 over A. And then the integral of d theta there is just going to be theta. Remember that this gave us 1 over A. Theta there, unlike before, now since we said x is equals to A tan theta, in this case, you have to first say x over A is equals to tan theta, so that theta would have to be equals to tan inverse of x over A. Then get that expression for theta and place it here. You get the standard integral for that form as 1 over A, and then tan inverse of x over A. So this, if you memorize that standard shape of that integral, which is this one here, if you memorized it, it implies that if you're given something like, okay, find the integral of 4 over maybe 9 plus, this can be y squared dy. Just know that the 4 here is not affected by the integral. And apart from that, from the 9, the A becomes 3. So it's the same as pull out the 4 from the integral comes here. This is now 1 over that. So that your answer will have the 4 multiplying the solution of this. A being the square root of this term here. And y must have a 1, not a number. Once you've ensured that this becomes 1 over the square root of 3, which is of 9, I mean, which is a 3. And then you have tan inverse of y over 3. That becomes the solution. Without having to integrate, all I had to remember is this shape. Is that better, Mapalo? Yeah, so you just have to memorize. This is for tan substitution. You have to get also when sine works, how would it look like? And then also for the hyperbolic ones as well. Okay, so where are we? We even forgot what we were doing. Oh yeah, separation of variables. We just worked out one example. And I think that was the second example on separation of variables. Now what you have to do is you have to see that the same methods we have used can also work here. They can also work here. They can also work here. You can all work there. All you have to do is separate the variables. Now, for the next few examples, I'll just separate for you and try to make sure that you guys understand how it goes. And the one I think that I'll separate as the last example here is going to be number 3. Can you guys choose? Do you want us to separate number 3? Then you guys will integrate later. Or we separate number 5, then you integrate later. Which one do you want to see? Oh, they are all basic. You can pull them off. Number 3. Okay, let's get number 3. So for number 3, what we have is dy dx is equal to 1 plus y to the power 3 over x, y. Then we have, that's y squared. Then we have 1 plus x squared is equals to 0. Okay, that is not an equal sign. This is a plus here. So this is what we have. Again, separation of variables, straightforward. Let's see if it is straightforward indeed. Okay, let's begin. So again, everything with x has to be on one side, everything with a y has to be on the other. So for now, I'll take the second expression, this term here to the right, it becomes negative. So I have dy dx is equal to negative, then I have 1 plus y to the 3 over x y squared, then I have 1 plus x squared. So this is what I have. Now, I want to separate these variables here. So just, see, the problem is this side here. It's like I have x's and y's mixing up. So what I'll do is that I'll group them up. I'll try to separate them just on that side. Notice that this whole part, I'll treat it as one term there. So that now I'll have minus. I'll bring out that 1 plus 3. I'll take it out. I'll bring it here. Not 1 plus 3. 1 plus y to the power 3. And then in the denominator, I see that I only have one y there in form of y squared. So I'll say this is over y squared. Then next up, what remains? Well, in the numerator, then there's nothing really that is going to be over the terms with x. So I'll just say this is over 1. And then I have this x, which is outside. So I'll say there's an x here. Then I have 1 plus x squared there. Notice that I can quickly multiply these and they'll still go back to this expression here. You can do this in so many different ways, guys. And this is just how I feel it will be easy, because now I have grouped what has y and what doesn't have y. Now, what do I need? I need to get everything that has y to go to the left side. What has x, I'll leave them here, because that is where I'll bring the dx. I'll take the dx to the right side. But I just want to get everything that has y, this whole shape, I need to get it to the left side. There are two ways of getting it to the left. I can either divide by this same expression, and it will go there. So let me first get my dx to the right. Dx to the right, it means that I'll multiply by dx. Now I have minus 1 plus y. I'm just doing this step by step, guys, but really I can do this step and the next step at once. And then this here we have the dx. Now I can say divide the left and the right by this expression. I just have to know that the y squared goes up. The 1 plus 3, I keep saying 1 plus 3, 1 plus y to the power 3 comes down. So this will be over 1 plus y to the power 3 comes here. Then I'll say this is equal to, I'll maintain the negative being on the left-hand side. Now this is x, 1 plus x squared here. Then we have dx. Do you see that we have separated the variables? Can you kindly scroll up? Pardon?
Somehow I don't know if it's cross multiply to the dy for you to get that, yeah, y squared dy.
Okay. So I can just say, I think the easiest that you can get is just say divide both sides by this term. So now I have 1 plus y to the power 3 over that's y squared. So at this side, it will cancel with this, but on the left side, it will remain. Now I'll just want to make this a single fraction. As a single fraction, what happens? It's like I have dy divided by 1 plus y to the power 3 over y squared. Change this to multiplication. It becomes y squared over 1 plus y to the power 3. You see that? That's how it gets there. Have we answered that question? Okay. Then Mapalo, you wanted us to scroll up to which stage? Have you seen what you wanted to see, Makola? Just there, okay. So, any questions? I don't see how you simplified it. Which part? So, yeah, let's see. So this is just multiplication, really. I think I'm guessing you're talking about this part. It's completely up to you. I can do it in so many different ways. I think let's use the one that you guys like a lot, cross multiplication. So let's put it here. If I was to cross multiply here, then what it means is this will cross multiply to go to the right. This will multiply the dx. So I'll have x, y squared, 1 plus x squared, multiplying dy. On the right side, I'll have the negative first. Then I'll have 1 plus y to the power 3, the whole lot multiplying dx. Now, I want to eliminate everything that has x, bring it to the right. Everything that has y, bring it to the left. So what do? Let me start with making sure that, let's start with y. Let's take y to the left. So I want to get rid of this part, take it to the left. So I'll divide the whole expression by 1 plus y to the power 3. This sorts out this part, and then it remains on the left side. Now I have xy squared, 1 plus x to the power 2 dy over 1 plus y to the power 3 is equals to, so now we just have minus dx. Next up, I now want to get rid of everything with x from the left so that it ends up on the right. What has an x? It's this same x here and this bracket here. I can actually even combine them if I want, but this y must remain this side. So to do that, I can just say that, okay, divide both sides by what? By x, 1 plus x squared. The goal here is to make sure that they cancel here. But what I do to the left, I must do to the right. So here, I'll also divide by x, 1 plus x squared. On the left side, I'll now remain with only y squared over 1 plus y to the power 3 dy equal to minus dx. And then here we have x plus, no, not x plus, x 1 plus x squared. So now we have separated. So this is another way that we could have separated these. Are we okay there?
Yes.
Okay. So notice that even the next example, which one is that? Even part 4 as well, it's the same technique, just separate the variables. There's so many ways that you can do this. Even this one, same technique. So that now all you have to worry about is how you integrate them. Okay, so this sorts out separation of variables. The next part is homogeneous differential equations. How do we test for homogeneity?